Another interesting phenomenon that arises because of the wave nature of light is called diffraction. And this lecture will find out what that is. All right, so what is diffraction? When a wave moves through a hole in a barrier, like this guy over here, it sort of spreads out on the other side of that barrier. And you might have noticed that if you ever were at a lake or something and there was a seawall with a little hole in it. You can see the way that a wave spreads out through a hole like this. And this is really just Huygens' principle in practice, right? We said, what is the wave front here? Well, really, it's the sum of all these little wavelets, right? And so if there's a disturbance right here, that creates a new circular wave here. And there's no waves being created over here to cancel these out. So instead of getting a nice straight wave front that we get over here, you end up with a wave that looks like a wave, right? That looks like a disturbance right here that creates a wave spreading out in a circular direction. Now, most of the time we don't notice that because even if the opening is modestly big, there's enough little wavelets being created here to destructively interfere in the center, and then it looks like a straight line. So we only see this on the edges here, and we particularly notice when the size of the hole is the same magnitude of the wavelength, right? So sound wavelengths are relatively long compared to light wavelengths. Light wavelengths are super short. And so when you think about a sound wave going through a door here, um, it's going to spread out around that door in large part because those sound waves, because you get diffraction, right? It doesn't just shine in a straight, or the sound doesn't go through here in a straight line here, but instead it turns around the corner and the person over here can hear somebody who's talking. Okay, so that hole there in the wall is closer to the wavelength length of sound, and so diffraction there is noticeable. Now compare that to what happens when light shines through a door. We see a sort of straight edge there. We see very little diffraction there if light is shining through a door because it's got super small wavelengths, and that diffraction is just not very noticeable there. There's a little bit, like if you look carefully, right, when you see light shining around a corner like this, you'll see that there's a little bit of light in here, and that's the result of diffraction, but it's mostly washed out by the larger light that's not diffracting. Okay, so that's why you can hear around the corner of a door frame, but when we look at light around a corner, it makes a nice distinct shadow. So why is diffraction important? Why does it matter? Well, we're going to do a little experiment here, and this is called a double slit experiment because it's got two slits. And we're going to take coherent light. That is light that we know has the same frequency and wavelength and that is the same phase. So everything's in phase with each other. And we're going to shine it through these two narrow slits and see what happens. Now, if light were just a ray or a particle, we would expect it to go through the slit and make nice two little lines on this wall over here. But that's not what happens. Instead, we get what is called a diffraction pattern. Okay? If these slits are narrow enough, in other words, if the opening is near the wavelength side of light, okay, where we get a lot of the effects of diffraction, then instead of two lines over here, we get a diffraction pattern that looks something like this. Now, why does that happen? Well, if you think about the wavelets being created, right? My light hits here. There's a disturbance right here that creates this set of semicircular wavelets. There's a disturbance right here that creates that semicircular set of wavelets. And what happens is when they hit this wall, if both of these waves hit the wall in phase, then you're going to get a bright spot. In other words, if the distance from here to here, say, is 7 wavelengths, and the distance from here to here is exactly 6 wavelengths, then you're going to have the amplitude of both waves is going to be high and positive at the same time, and they're going to constructively interfere here. Okay, what happens though if this is 7 wavelengths away right here and this is 6.5? Well, in that case, this wave is going to be high and positive when it hits the wall here. This wave is going to be halfway through a wave, and so it's going to be high and negative right here. And these two waves are going to destructively interfere, and you get a dark spot. Okay, so it has to do with the fact that wavelets are coming out of these two spots and that they're going to interfere in different ways along this line. So let's look at that a little bit more carefully. Why do we have some bright spots? Okay, we've got a nice picture here of our wavelength. So instead of looking at the wavelets, we're going to think, okay, in this direction, this is what my wave looks like as it moves from point A to C. And this is what it looks like from point A or from point B to C. The key difference is the length of that distance from A to C and from B to C. Okay, they're going to interfere constructively. That is, they're going to be in phase with each other when they hit C if the length is an even number of wavelengths from B to C and an even number of wavelengths from A to C. Okay, so if they are in phase here, right? Remember we had coherent light shining through this. So they started out in phase and say, let's see how many wavelengths we've got. 1, 2, 3, 4, 5.5 wavelengths to get from B to C. Here we've got 1, 2, 3, 4.5 wavelengths. So they're going to be here constructively interfering with each other at point C, because the distance between them is exactly one wavelength apart. Okay, so when this wave is going up, this wave will also be going up, and you'll get a high amplitude. When this wave is going down, this bottom wave will also be going down, and so the amplitude of the full wave at C is going to be going up and down and up and down and up and down. That means a bright spot. That means your amplitude of that wave is high right there. Okay, D here is always going to be a bright spot, right? Because the distance from A to D is the same as from B to D. So if they're in phase here and they travel the same distance, they're going to be in phase right there. So we'll see, we can get a bright spot at D where that length is the same. And then we can also get bright spots where the distance of AC is exactly one wavelength between the distance of BC. Now, it can also be exactly 2 wavelengths different, right? Because if this is in phase at A and B, and they travel exactly 2 wavelengths farther, then it's still going to be in phase. And so you get a second bright spot up here. We define that as my here, where that m can be any integer. It can be 0, it can be 1, it can be 2, or it can be -1 down here. Okay, so we get bright spots that are relatively evenly spaced along here. And we could use some trigonometry to show that the difference in length between AC and BC is very close to d, this distance, times sine theta. And we're not going to dig into that trigonometry too deep, but what you find out is that we can come up with an equation for where those bright spots are going to be. Okay, we want to know what our angles are. What angles are going to define where our bright spots are? They're going to be defined by the wavelength of our light, by our integer number, right? So this defines which spot we're talking about. This is the 0 spot, this is 1, this is -1, this is 2. D here is the distance between our our slits, and then theta is going to be this angle here. Okay, so if we know d and we know the wavelength of our light, we can predict where each of those slots are going to be. Okay, if I wanted to find out where the 0th bright spot was, I'd put 0 in here, take my d for my distance between my slits, know exactly what kind of wavelength, that coherent light I'm using, and that would tell me what theta is. So I could define, as we see in this image, my first bright spot, I could define my second bright spot, I could define my third bright spot. And so those 1 and 2s are my m's. Okay, so that defines where we have constructive interference. That's where our bright spots happen. Now, the distance y between those bright spots depends not only on these factors up here, but also this distance L, right? This equation defines theta. So if I make L bigger, then the distance between the bright spots here are going to get bigger. As L increases, the value of y, that is the distance between my bright spots, also increases.